third way that energy can be transferred is through radiation. Unlike the other two, radiation, it's given off in the form of electromagnetic waves. Light is an electromagnetic wave, but also radio waves, microwaves, UV, X-rays, gamma rays. And because it's given off in the form of electromagnetic waves, it doesn't require a medium, meaning it doesn't need something to travel through. Unlike the other kinds of convection and conduction both require some kind of material to be there, but radiation can occur even in vacuum. All objects radiate energy into their environment. For most objects, this winds up being mostly infrared, unless they're really bright. Many objects radiate in the visible spectrum, so there is something called an optical pyrometer, which is kind of fun to say. An optical pyrometer, it determines temperature based on what wavelength is being radiated. No doubt you've heard of something being red hot, and that corresponds to a particular temperature. If something is radiating red, that's about 800 degrees Celsius. Examples being your oven coils, and also one of the largest stars that we are aware of, Betelgeuse, which is a red giant star. And as far as we can tell, it's huge. Red giants are pretty big. And objects radiate yellow if they are between about 3,000 degrees Celsius and 6,000 degrees Celsius. This is the temperature of a light bulb filament. If you have, I know we have all fluorescent lights in school, but at home, or maybe at home you even have fluorescent lights too, but you guys know what a light bulb filament is, I hope. And then also our sun, as you know, is yellow. And then blue is the shortest wavelength, highest energy color we can see. That's between 10,000 and 30,000 degrees Celsius. And nothing on Earth is really, normally that hot. But there are a couple of stars, Rigel and Procyon. I think it's Procyon. I don't know how to pronounce that. These are two stars that are visible, and they're two of the brightest stars in the night sky that we can see, or that we could see if we weren't in the middle of a giant city that has air and light pollution. But if you go outside the city, these are two of the brightest stars in the night sky, and actually even here, I think you can see them sometimes. But the power of a source radiating, and remember, power is energy per time. Power is proportional to its surface area, and also to temperature to the fourth power. I don't really know why it's to the fourth power, but it is. The equation is this: E, and this is the Greek letter lowercase sigma. Sigma is sum, the capital sigma, but this is lowercase sigma. A t to the fourth. The A is the surface area. The sigma is called the Stefan-Boltzmann constant. Or does Boltzmann have one M? I think it's two N's. And it is equal to 5.67 times 10 to the 8th. This is a constant that's easy to remember, 5, 6, 7, 8. And the units are goofy, as they are with many of these constants. Watts per meter squared times Kelvin to the fourth. All right. And E for an object is called the emissivity. And it is a number between 0 and 1. An emissivity of 0. An emissivity of 0 means no energy radiated. Emissivity of 1 means it radiates perfectly. Oops. So emissivities of 0 and 1 are idealizations, but there are some things that are pretty darn close. Lighter colors tend to have low emissivity, and darker colors tend to have high emissivity. And interestingly enough, emissivity also determines how much energy an object absorbs. So things that absorb energy more efficiently tend also to radiate energy more efficiently. And how they absorb energy has to do with the temperature outside. So the net power radiated is equal to same thing, but then you have this T to the fourth. This is the T of the environment. This is the temperature of the surface. Okay, and so the amount of energy absorbed is just E sigma A times temperature of the environment to the fourth. The amount of energy given off is E sigma A times temperature of the surface to the fourth. So this gives you how much power is radiated out into the environment. Okay. So you can plug stuff into there and get numbers for that. Now, E is the same for absorption and emission. A perfect emitter, absorber, this is known as a black body, and we'll talk more about black bodies later on. And this is called an ideal reflector. So no energy is absorbed because it reflects all the energy. A reflector, you may have noticed that those like metal water bottles, a lot of times will have a shiny reflective surface, and that's because then the water or whatever is inside of it, and also mugs for like coffee and stuff, that means that whatever's inside of it will not really radiate or absorb energy. So if it's cold, it'll stay cold. If it's hot, it'll stay hot. A lot of times those water bottles also have a layer of vacuum in between two layers of metal, and that makes it basically impossible for conduction to occur, because conduction requires a medium, and so those metallic thermoses can be pretty efficient at keeping a drink cool or hot, depending on what you want. This lighter and darker thing is also interesting. If you look at cultures where people live in the desert, you'll often see them wearing like light-colored robes, and the reason for that is that the emissivity of light colors is closer to 0, which means that they're absorbing less energy from their environment. Now you also see some places where they will wear darker robes in the desert, and really what that has to do with is temperature. If it is hotter outside of your clothes than your body temperature, then you're better off wearing dark colors, because you'll be able to, there will always be heat conducting into your clothes if it's hotter outside your clothes than it is inside your clothes. And so you just get hotter and hotter, but if you have dark clothes on, then you radiate more efficiently, and more of that energy will go back out into the environment. If it's hotter inside your clothes than it is outside your clothes, then you're better off having lighter colors, so you don't really absorb energy from your surroundings, and then by conduction the heat will flow out away from you. So that's why you see different desert tribes with different types of different colors of clothing, and that's either light or black.